Good day everyone. So our topic is all about the geometry of inversion. In this video, we will tackle all about the basic concept as well as the additional properties and invariants under inversion. So we were discussing inversion. So here is the standard circle which is of a radius 1. So let's name it O, and this radius is 1, and we discuss this. There is a rule of sending points or moving points on the plane. Maybe I can write that there is a rule of moving points the plane, and that the rule is known as inversion. And what was the rule? I will give you an input that is point P. Suppose this one, and you will apply this rule. Whatever rule, specific rule that I describe, it will get the output point called P prime. So this is the output P prime. So what was the rule? The rule was pretty simple. It said that if I join OP and produce it, so may we again join OP and produce it in the direction of P. So in this direction, find the point P prime somewhere out here, such that, or maybe I can call this P1. Let's call this P1, and the only condition that it needs to satisfy is OP times OP1 is equal to 1. If this happens, if we find such a point P1, then that will be my output, and this P will be known as the inverse of P. All this we discussed in the previous discussion. So let's assume in the previous discussion that we had in this sequence. Now the question is, how can we geometrically find out the inverse of a point? And you can understand why this point P1 called the inverse, because after all of your multiplying OP with OP, you are getting 1. So if the two numbers, so as you can see to the presentation, if the two numbers are multiplied, one of them is the inverse of the other. So this also gives you a geometric way of sort of finding out the reciprocal of numbers. So given a point P, how would you construct its inverse using straight edge and compass? So let's see how we can do that. Let's take the reference circle one more time. Maybe again, just use a little bit more care to draw the circle. So this is the circle. Maybe something like this. So let's suppose this point is all the center, and we are trying to find the inverse of the point P. And we are allowed to use only two things, compass and the straight edge. So the question is, how can we do it? So in this video, I'll give you the recipe or the method of doing this, and I'll ask you to actually prove it that you can do it and this method works. In the next discussion, we will explain why the method works. So the first thing you have to do, that step 1. So yan, step 1. So we will do the step 1, which we need to join OP. So let's see if we can join OP. Then let's suppose this point is the point of intersection OP, the circle. So join OP. So step 2 is from the point OP, or the from the point P, rather draw a tangent line to the circle. So you can draw two of them. So like this. So yan, yung red. So like this, of course, this will work. This will work only if P is outside the circle, but this process can be modified so that it works for points inside the circle. So draw the tangent from P to the circle, whatever is the point of the tangent. So let us call P and Q. Join PQ. That's the third step. So let's proceed to step 3. Join PQ at this point. This is our inverse. This point P1 is our inverse. So have you have you to prove is OP1 times OP is equal to 1. That's the P1 that we have got from this process. OP1 times OP would be equal to exactly 1. So prove that, and you would also have to know why. Okay, I think I made a mistake. So I named these 2 points, both of them as P, so maybe I can change the point. So we will change the point. So let's say, I will erase that one. So let's say MN. So that's an easy fix. So call this MN, alright? So first, prove that OP1 times P is equal to 1. The P1 that we have got from this process, and then also find a method to draw a tangent line using a compass and straight edge. So how would you actually draw the tangent line? Because you have that, and that's the second step, you have to draw the tangent line. So now, in order to find the inverse, so in this construction, geometric construction, which is still part of the inversion, that's a vital step. Joining RP is easy. You can do it with a straight edge joining MN, and also needs just a straight edge. Sorry. Drawing the tangent line would require more than that. So okay. So let's look an internal point. So this is the internal point. So instead of working with the external point, this one, the circle, we will look at the internal point and try to find its inverse. So again, this is the reference circle. This is the point O, and suppose we are looking for the point P, which is here. So again, join OP and extend it to meet the circle at some point. As so, the step 1 is same, join OP and extend it. So maybe like this. The step 2 is the drop of perpendicular, or rather erect a perpendicular at the point P. So erect perpendicular at P. So maybe I can draw this. So erect perpendicular at the point P, and suppose this point is MN. And the third step, draw a tangent at M. So draw a tangent to the circle at M, and suppose it meets the extended lying at P1. Then the P1 is your inverse. So if this is something you have to prove, again, so here to try both for the external and external point. So the internal and external point, try the geometry construction also, and it also works. And of course, you have to show um, that how to draw a tangent line using a compass and a straight edge. You can do that, and I have to show that both of these things together will give you a geometric construction of the inverse of a point. And now in the next discussion, we will actually show this construction works, and also give a recipe to construct a tangent lines using compass and straight edge. That will finish up the construction of the inverse of point once and for all. Keep doing great mathematics, and I'll see you in the next discussion by Sir June Ampolokyo. So let's wait for the next discussion or next topic. So thank you so much for listening.
A pleasant day to everyone. I'm John Albert, the groupmate of Sir Absar, in lecturing about the geometry of inversion. So we'll be integrating the analytic geometry of inversion. Before we dig into our main topic in this lesson, Let us define first what is analytic geometry. It is also called as coordinate geometry, wherein it is a mathematical subject in which algebraic symbolisms methods are used to present and solve problems in geometry. So basically, we're using points of coordinates and formulas in solving problems. Let us review also the inversion. So talking about inversion, it is the transformation of a point or points. We denote it previously in our lesson, point P, to the corresponding set of points or point. We denote it as P prime, known as their inverse point. Okay, previously, Sir Abzar explained this equation. Okay, let us illustrate it in a coordinate plane. So this is our x and y axis. Okay, this is the inversion circle having the point P prime at the outside. Okay, the coordinate will be x prime and y prime. Suppose that our center of inversion is at the point of origin having the coordinate of 0, 0, and we denote it as O. And this is our point, okay, having the coordinate of x and y, suppose. Now, if we are going to find the length of 2 points or a line segment, what formula are we going to use? Okay, this is our radius. Now we are using the distance formula. So the distance formula is the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Okay, how are we going to find the length of OP? So in this case, our x sub 1 will be 0. So in this case, we are pointing the the point O, our center of inversion. Now, our x sub 2 is x, wherein it is the coordinate of P, and the same thing, our x sub 1 is 0, and our y sub 2 is y. So upon simplifying, we are having the value of OP is equal to square root of x squared plus y squared. So OP prime is equal to square root of the quantity of x prime minus 0 squared plus y prime minus 0 squared. And simplify, we are having the value of OP prime is equal to square root of x prime squared plus y prime squared. And let us substitute the value of OP and OP prime. So we're having this equation, the quantity of x, the square root of x squared plus y squared multiplied by the square root of x prime squared plus y prime squared. To continue, so this will be the equation. And what we're going to do next is that we're going to extract the square root. So we're going to square both sides. So this will be now the equation. The quantity of x squared plus y squared multiplied by quantity of x prime squared plus y prime squared is equal to r raised to 4. Since O, P, and P prime are collinear, therefore these 3 points are lying on the same line segment. Therefore, our x prime over x is equal to y prime over y. Cross product property. So we have x prime y is equal to x times y prime. And square both sides in order to, our objective in here is to find the value of x prime squared. that we're going to substitute in this equation. Okay, so moving on, so we are having the value of our x prime squared is equal to this expression. Now let us substitute the value of x prime squared to this equation. So in this case, we are having this equation, quantity of x squared plus y squared, quantity multiplied by the quantity of x squared y prime squared over y squared plus y prime squared is equal to r raised to 4, and then factor out. So we are having what we're going to do next is we are going to factor out the y prime squared over y squared multiplied by the quantity of x squared plus y squared, and then another x squared plus y squared, and simplify this expression. So we are having an equation of y prime squared over y squared, quantity of x squared plus y squared raised to 2 is equal to r raised to 4, and then let us multiply both sides by y squared and simplify. Therefore, we're having this equation, y prime squared, quantity of x squared plus y squared raised to 2 is equal to y raised to 2 r raised to 4, and square root both sides to continue. So this is our equation earlier. So our main goal is to find the y prime. So in this case, uh, we are putting square root both sides. So and simplify and divide both sides by x squared plus y squared. Simplify. Therefore, the value of our y prime is equal to y r raised to 2 all over x squared plus y squared. So this will be now the value of our uh, y prime, which is the y coordinate of the inverted point. Hence, if we are going to substitute earlier's equation, this value y prime squared, the same process, took the same process and substitute to this equation, right? This expression is being substituted to this uh, y prime squared. The same took the same process. Therefore, we are having the value of x prime will be equal to uh, x r raised to 2 all over x squared plus y squared. So the that we undergone earlier is a formulation of this theorem. Uh, 6.10 stated that the equation for the inversion transformation of a point P having the coordinate of xy into P prime, which is our inversion point, uh, having the coordinate of x prime, y prime, relative to the circle x squared plus y squared. So this will be the value of our x prime, uh, and our y prime is this one. Okay, let us illustrate. So this will be now our theorem. Okay, on the other hand, the result of x and x prime will be interchanged, and y and y prime can be interchanged, so that the formula of our x will be now x prime r squared all over x prime raised to 2 plus y prime raised to 2, and our y is equal to y prime r squared all over x prime squared plus y prime squared. Okay, now let us apply the theorem 6.10 in order to solve the example. So in this example, we're going to find the inverse of point 1, 1 with respect to the circle. The equation of the circle, x squared plus y squared is equal to 4. But before we dig in, let us solve first what is the length of our radius. This 4 is equal to the square of the radius. Therefore, r squared is equal to 4 based on the equation of the circle. So the length of our radius, what we're going to do is this equation is to square root both sides. Okay. Okay. Now the value of our r or the radius is positive, negative 2 units. Okay. Now let's illustrate the circle. Okay. In a coordinate plane wherein our point is at 1, 1. Suppose that we denote this point P, and then our inversion point is at denote it as P prime. So let's connect it by ray. So upon illustrating, since it is being said that the length of this radius is 2 units, and by that we are able to illustrate our circle. Okay. Looking back to the formula, so the x prime is equal to xr, or the radius raised to 2, all over x squared plus y squared. And let us substitute the value. Now, the x value is this one, or the coordinate of our p, and our y value is this one. Okay, now let's substitute the value. So x equal to 1, therefore it will become 1. Our r, okay, or the radius will be positive, negative. It's up to you what you're going to use. But then since it is being squared, so still the value of this part is positive. Okay, if we're going to simplify, therefore, uh, if we're going to simplify, the value of our x prime is uh, 2. Okay, next let's move on to our y prime, or the point of inversion to complete the coordinate of the point of inversion. Now looking back again to our theorem, so the formula of y prime is equal to y r squared all over x squared plus y squared, and it is being denoted that the value of our y is equal to 1 right here. It is given, and the value of our radius is plus minus 2. Okay, moving on. So positive, negative 2, value of our r, and y value is equal to 1 over x is equal to 1 right here. Okay, and our y is also equal to 1. It's given. And simplify, so we're having the value of our y prime is equal to 2. Therefore, the point of inversion, which is we denote it at p prime, is at, okay, 2, okay, 2 at the point 2, 2. If we are going to plot it in a point, so right here is the point of inversion. Now to answer the question, so the point of inversion at 2, 2. So this will be the answer. Okay. Now there is a question. What if the center of inversion is not in the point of origin? Okay. What if it is being placed at 1, 1, or in first quadrant, the second, the third, or the fourth quadrant? So that's the question. Right, to answer that particular question, it underlies the application of standard form of the equation of a circle. at the center of HK. As we all know that the previous solutions, if we're going to utilize this equation of the circle, probably it deals with uh, this equation. Same thing will happen. Then if you're going to substitute it by means of the previous theorem, okay, the same value that we're going to obtain. So in this case, if we are going to substitute the value of our x, wherein it will equal to x double prime minus h, and our y is equal to y double prime minus k, the same result going to obtain. So by this formula, I'm able to solve uh, an equation which is not in the center point. Okay. For example, find the inverse of 0.11 with respect to the circle. Right? This is the standard form of our inversion circle. So having the center at 2 and 2, which is the h, okay, the center point, it's hk, changing the sign, and having the radius of 4. I mean, the 4 in here is the r squared. Okay, r squared is equal to 4 based on this the standard form of the equation of the circle. By this, if we're going to find the length of the radius, so square both sides, the same process are there. Okay, and our r will be the square root of 4, probably plus minus 2. Okay, that's why plus minus 2. If we are going to illustrate it in a Cartesian coordinate plane, this will be the figure. So, uh, upon applying the formula which we substituted earlier, this will be our x double prime, and this will be our y double prime. So by this, if we're going to substitute these value, okay, this one and this one, in this formula, okay, the result will be inverse at point negative 2 and negative 2. Where is it? Right here. Okay, suppose that we're going to denote it a prime. This will be the point of inversion from starting at the point in here and going through this. Okay, so that's it. Inverse it at this point, negative 2 and negative 2. Alright, okay, moving on. What if we are going to solve the inverse value of a complex plane? So that's the question. Another theorem that I'm going to introduce to you, the theorem 6.11, wherein it is stated that transformation of points in the complex plane with respect to the unit circle with the center of at origin has the equation of z prime is equal to 1 over z bar. Okay, where z bar is the conjugate of z. If z is equal to a plus b iota, okay, I or imaginary number, then if we're going to illustrate it, the same thing will happen. And z prime is equal to 1 over z, wherein if it is the conjugate of z. So it is equal to 1 over a minus bi, having its conjugate process. So we are going to multiply by its conjugate. Therefore, this will be the value. Okay, so z prime is equal to a plus bi all over a squared plus b squared. Right? So for example, let's move. All right, for example, if we're going to solve this, the inverse of 2 plus 4i with respect to the circle with center at origin and radius of 3. Upon having the equation of our inversion, so we have x squared plus y squared. And since the radius is 3, this right portion of our expression will be r squared, and if we're going to square the 3, it will become 9. So for the solution, so we're having this as our r squared, okay, and the denominator is this value. On having the conjugate, this is our z here, and the conjugate of it is going to multiply both numerator and denominator by 2 minus 4i, imaginary number, 2 minus 4i. If we're going to simplify, so we're having 9 quantity of 2 minus 4i all over 4 minus 16i squared is equal to quantity. Okay, let's distribute the 9, become 18 minus 36i all over 4 minus 16. And then, as we all know that I squared is equal to negative 1 because the square root of negative 1, okay, raised to 2 is equal to negative 1. Okay? All we need to do is to crush out the squared and the squared. Okay, if we're going to simplify, so we are having the value of 18 minus 36i all over 4 plus 16. Then let's simplify everything. So 18 minus 36i over 20. And let's separate the fraction. So 18 over 20 minus 36i over 20 is equal to, let's simplify the first fraction. So we're having 9 over 10 minus 9i over 5. Let's move on to the application of inversion. So these are some of the application of inversion. First is the theory of poles and polars, wherein it is used in projective geometry. Okay, this will be the illustration. Next will be the Mascheroni construction. So it employs construction in the inverse point as a basic technique in order to carry out many other constructions. So these are the illustration, sample illustration. Okay, next will be the finite geometry of the Sarg. So use the concept of poles and polars. So this will be the illustration. A new fact about inverse point shows an application to an earlier construction problem. Okay, this theorem I'll be introducing. Okay, 6.12. It is stated that two inverse points with respect to a circle divide the diameter on which lie internally and externally in same ratio. So this will be the illustration, and if we're going to multiply OC, okay, this length OC multiplied by OD, okay, it will be equal to the squared of OB. Okay, the same application earlier as it is being explained to by explained by Sir Abzar. So by this, we're going to divide both sides by OB. So we're having this proportion. OD over OB is equal to OB over OC. Okay. By the application of theorem on proportion, if A over B is equal to C over D, then A plus B all over A minus B is equal to C plus D all over C minus D. Let's illustrate. Okay, wherein B is equal to C, and then our A is OD right here. This, okay, OD, and our B is OB, and our D is OC, right? So let's substitute these value. OD is equal to A, so OD plus OB. OB is B, and all over OD minus OB. So from this proportion, so substitute the value of our B, which is also equal to C. So substitute reflexive property of equality. So OB plus OC. OC is the value of D all over OB minus OC. And then upon interpreting the illustration, so OD, right, length of OD plus OB is equal to AD, because OA, okay, this length is equal to OB because they are radius, right? Get my point? So in the denominator, OD minus OB is equal to BD, is equal to AC, okay? The value of AC in here is OB, okay? OB plus OC is equal to AC. Get my point? The same thing. OA is equal to OB. And the denominator, OB minus OC, is this length, CB. Okay? Therefore, we're having this proportion, AD over BD is equal to AC over CB. That's it. The fact that an inversion transformation sometimes transforms a straight line into a circle or a circle into a straight line is the basis for physical application of inversion and linkages that change linear motion into uh, curvilinear motion or vice versa. The harnessing of the tides, the driving of a locomotion or a locomotive, and the production of electricity of an illustration of one type of motion change into another type of motion. So the mechanical problem of devising linkages to do this sort of things has concerned engineers during the past hundred of years. So such device is called the Fusilier cell or Fusilier linkage. A linkage with six rod which draw the inverse of a given curve, the quadrilateral. Okay, let's illustrate. So this quadrilateral A, P prime, B, and P. Okay, this is quadrilateral, is a rhombus, right? So it means that the distance of AP prime, P prime B, BP, and AP are congruent. So OC, okay, this line segment is perpendicular bisector of AB. Okay? It is bisecting, therefore AC, okay, and BC are congruent. Okay, these are congruent. The sides are congruent also. So that's it. That's the concept of Poiseuille cell. If we put it in an equation, OP times OP prime is equal to the quantity of OC minus PC, quantity of times the quantity of OC minus CP prime. Let's apply the the geometry of inversion, okay, upon simplifying, right, discussed by Sir Abzar. So we're having this equation, OC squared minus PC squared, okay, from this inverted point to this simplified point, which is probably the what do you mean the radius of a circle. All right, moving on. So let's simplify everything. So a squared minus ac squared. In this case, we are applying the Pythagorean theorem. Okay, this is a Pythagorean theorem, and then if we're going to simplify, so we have OA squared minus BA squared. Okay, since we're going to subtract this, okay, then simplify. So we are having the value of our OP times OP prime is equal to OA squared minus BA squared. Okay, let us watch what how it works. Okay, how it works. The Poiseuille linkage is the illustration of the Poiseuille uh, linkages. Okay, as we all know, this is the P, right in here, this one, and this is our inverse point, and composing a six rod. Okay, one, two, three, four, five, and six. So as we observe in here, it is uh, the inversion circle, and this will be the radius of the circle. So as we all know, we're creating a circular motion in here, and this one, as we can see, it creates an upward and downward uh, motion. So that thing explains how Poiseuille linkage. A different application of inversion is that of finding new theorems by inverting familiar ones. More precisely, the figure for a familiar Euclidean theorem, when inverted, may yield a new theorem suggesting the corresponding properties. Even further, the new theorem does not have to prove from the beginning. It is true because of the proof of the origin theorem and accepted properties of inversion. For example, we'll illustrate the technique. One of the elementary theorems from geometry is the statement that if a line is perpendicular to a radius at its endpoint of the circle, then it is tangent to the circle. A new theorem by inversion comes from taking the circle as the circle of inversion. It is stated as this theorem, 6.13, stated that the circle whose diameter uh, is the radius of the second circle internally to the second circle. So if we're going to illustrate it, okay, this one. So the more elementary theorem, it is illustrated in this figure. So it is very important to realize that the new figure is concerned only with the relationship among the image set of points. It is not concerned with the relationship between the origin original figure, and the new, nor the with areas and other extraneous factors, but only with the relationship within the new figure that makes it possible to state a new theorem. Suppose in this illustration, DE is the image of OC. Okay, this is the image of this radius. Whereas the circle with diameter BE, okay, is the image of AB. The circle of inversion is invariant. The fact that AB is tangent to the circle means its image a circle. Okay, is also the tangent to the circle of inversion since angles are preserved under inversion. Okay, on. So by that, it explains the theorem. So another theorem that I'm going to share to you, the theorem 6.14. Okay, the new theorem will involve four circles, and the conclusion will be that two of them are orthogonal. Okay, this new theorem valid in Euclidean geometry is stated in somewhat complex wording. Okay, so let's state the theorem. If circle 2 is orthogonal to the circle 1, if circle 3 passes through the intersection of 1 and 2, and also intersects circle 1 in another distinct point, if circle 4 passes through the second intersection of circle 1 and 2, and the second intersection of circle 1 and 3, and if circle 1 I mean 2, 3, 4 having another distinct point in common, then circles 3 and 4 are orthogonal. Okay, let us illustrate. This is the perfect illustration of this theorem. So in the discussion thus far, inversion have been used to the new theorem from old. In general, the new theorem has been more complicated because some of that straight have been inverted into circle. In the application of inversion, called proof of inversion, the procedure is somewhat reverse. I mean, here the idea is to prove more complicated theorem by inverting the figure and then using simpler theorem already established. So the classic example is the proof of Pushback's theorem, which is another theorem that I'm introduce. Okay, the Pushback theorem. It is stated that the 9-point circle of a triangle is tangent to the end circle and to each of the three x circle of the triangle. So in this figure, okay, let I and I prime in the center of the inscribed circle, and any one x circle with a prime, okay, this one is the center of BC, okay, at the center of BC. So if ID, the length of the radius of the smallest circle, and IE, okay, this one, also the radius of the uh, the bigger circle, is perpendicular to BC. Okay, it creates 90 degree. So BEI prime is a right angle, who's also the midpoint of D. Okay, DE. This can be shown as the result the fact that BC is congruent to CE. Okay, this is congruent to BC. Now, since both have measure equal to half the perimeter of triangle minus the length of AC, now if A prime is taken as the center of inversion, okay, the A prime as the center of inversion, and if A prime D, okay, this one, the A prime, where is it? The A prime D, okay, and the uh, E A prime, okay, this one and this one, is taken as the radius of the inversion, then the encircle and excircle are both invariant since they are orthogonal to the circle of inversion. So the 9-point circle passes through A prime and F, okay, divides it externally. So with respect to the circle of inversion, it established that G, right here, okay, divides DE internally and the same ratio of F divides it externally. Thus, the image of the 9-point circle is aligned through G, okay, right here, because the angle preserved under inversion. So the angle between the image of the 9-point circle and BC is congruent to the angle that the tangent to the 9-point circle at A prime makes with BC, okay, this one, is congruent to the angle that the tangent to the 9-point circle A prime makes at BC. So it can be shown that this tangent is parallel to the opposite side of the orthic uh, triangle. So the triangle through the feet of the altitude. So right here. Okay, this one. This line is anti-parallel to the BC. So also shown as the two anti-parallel lines makes congruent angles with the bisector of the angle between the other two sides of the inscribed quadrangle, but it is another external tangent of the circle, and I prime makes same angle as BC and IT does. So it uh, is the tangent HJ right here, the HJ. It is the tangent of the two circle. That it is the image of the 9-point circle. This means that the 9-point circle is tangent to both encircle and excircle. In a similar way, the 9-point circle can be shown to the tangent to other excircle. Another example of the proof of inversion, I mean, going to chapter 9, which is the non-Euclidean geometry. Later, we'll be expounding it. All right, moving on. Corresponding to the inversion relationship by the line and the circle in two dimensions are those between plane and sphere in 3 dimensions. For example, provided with the next theorem that I'll be introducing, example of proof by inversion appears uh, in chapter 9 as we're about to to have the content of non-Euclidean geometry. In this inversion, it is used on the Poincare model for hyperbolic geometry. Okay, so to find the sum of the measure of the angle of a triangle. So right here is the illustration. Shows that P and P prime are inverse point with respect to the sphere of the radius, then OP multiplied to OP prime is the R squared. Same application previously. In this case, we are referring to the sphere or the three-dimensional uh, illustration. Inversion in 2 dimension can be seen in a cross section of 3-dimensional drawing with the same passing through the center of the sphere. corresponding to the inversion relationship between the line, circle, and the two-dimensional whose been the plane, okay, and the sphere in the three-dimension. An example is provided to the next theorem, which is probably the last theorem. Theorem 6.16 stated that the image under inversion with respect to a sphere of a plane through the center of inversion is a sphere passing through the center of inversion and conversely. So it is a special case of inversion with respect to a sphere known as the stereographic projection. It is very useful in making a map. So probably Google Map or Waze. So it is the fundamental basis, the application of this theorem of inversion. So this method of projection is illustrated in this figure. So plane A is the tangent to both and the sphere of O as the center and the sphere B as the center at the common point A. So plane alpha, okay, and the sphere with O as the center of inverses with respect to the second sphere. Okay, this is the first sphere and the second sphere. And the effect of this inversion is to establish a one-to-one correspondence between the points on the sphere and on the plane. One of the important features of the map prepared this way is all the angles measured are preserved under inversion. So it is also used in obtaining the Poincare model for hyperbolic geometry as mentioned earlier. So the inversion geometry of this chapter has proved very useful geometry in our daily living. Okay? Through the invariant properties are not all the same as those Euclidean geometry. So the two geometries do have many common concepts. The inversive and Euclidean geometry are distinct geometry in the sense that neither is a special case of the other. So the next two geometry that we're going to dig in, probably the projective. We're done already, I guess. The projective geometry and topology are generalization of the Euclidean geometry and includes it as a special case. So that's end as our part. Okay, so these are our references, and that ends our report. Thank you so much for listening, and God bless us all.